Good morning, class. Here's practice test number 3, module 3, covering chapter 6 and 7. We are looking at chapter 6, normal probability distributions, and we are continuing to the last part, the second half. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? So first and foremost, you're dealing with ND, normal distribution. Mu is 100, sigma is 15. So when we do word problems, we want to write what is given to us. Okay, everybody. And so that's what we start with. Okay, it's important to understand the given. And now we want the probability of X larger than 120. We go to the z-score, which is X minus mu over sigma. X is 120, mu is 100, sigma is 15, and that results in 1.33. So normal distribution, standard normal distribution, graph, we want z to be larger than 1.33, somewhere there. So we want this area. So clearly is less than 0.5. So we should recognize that. So we use technology table. We come up with the answer, and we are going to change it to the format they asked. So 0.0918 is the answer. We change it to 9.18%. What is the maximum IQ score for the bottom 30%? So we want the area to the left to be 30% or 0.3. So the area to the left must be 0.3. We are going to find the z, and then from the z, we are going to go to x. So if we go with the table, when z is between these two numbers, okay, gives us the 30% that we are looking for. And z is x minus mu over sigma. The cross product gives you x. I hope everybody can see this is elementary algebra. If I do the cross product here, okay, I can find x equals mu plus z sigma. So let's plug in. When we plug in, everybody, we're going to use a number in between if we are using the table. And pay attention to the fact that it's negative. So negative 0.525 times 15, and it ends up being 92.125. It must be less than mu. Why? Because this is referring to the bottom 30%. Right in the middle, 50%, z-score of 0. Z-score of 0 corresponds to mu equals 100. So maximum IQ score for the bottom 30% is this number, 92.125. In other words, if you draw a line, z-score of 0 corresponds to x-score of 100, which is the mean. And then this number, the z-score of negative 0.525, corresponds to the x-score of 92.125. Now, if we want to go with the inverse norm, we can even keep the mu as 100 and sigma as 15, and it will give us this answer. Needless to say, it's exactly the same within one decimal, but if you go with two, this is 92.13, and this is 92.13 also. If you go with three, then changes. So within two decimals, they're the same. Or you can find the inverse norm with a different mu and sigma. Mu is 0, sigma equals 1, and that will give you the z value. Okay, if you keep this as, we go with S and D, 0 and 1, this will be the value that we have here. This number, of course, more precise. You have to calculate the x. Could somebody read this question, please?
Men have head breadths that are normally distributed with a mean of 6 and a standard deviation of 1 inch. Oh, sorry. If a man is randomly selected, find the probability that his breadth is less than 6.2 inches.
Perfect. So again, word problem. What is given? It's a normal distribution. Mu is 6 and sigma is 1. It pertains to all men. Okay, it's not a specific size. So mu and sigma. We want the probability of x less than 6.2. We're going to calculate the z, x minus mu over sigma. So x is 6.2. We wrote mu and sigma as 6 and 1. We end up with 0.2. So we want the probability of x less than 6.2, which is the same as probability of z less than 0.2. This is normal distribution. This is SND, standard normal distribution. And if you go with the table, you locate 0.2 here, and you want this area. And from the table, we can find 0.5793 as the answer. Now we are looking at the same situation. Instead of 1, we are looking at 100 men. So otherwise the same situation. So I want to explain the difference. So if 100 men are randomly selected, we want to find the same probability that their head breadth mean is less than 6.2. In other words, we want the probability of x bar less than 6.2. So we want to distinguish between the two. Okay. So mean x bar. This is not the mean. And so what is the difference? Anytime n is any number other than 1, we have to go with x bar. N is 1 here. N is not. So n is 100. And whatever it might be. So the formula here is z equals x minus mu over sigma. But over here is x bar minus mu of x bar over sigma of x bar, where mu of x bar is equal to mu and sigma of x bar is sigma over square root of n. I thought we had this. That's how come I? Pretty strange to me. In any event, we are going to use the z-score here. 6.2 minus 6.0, 1 over square root of 100. And if you compare this to this one, you see, first of all, 1 over 100, that means 1 over 10. So it's a complex number. This gets multiplied by 10 in essence. So whatever this is gets multiplied by 10. This is elementary algebra. You get number 2. So this is normal distribution. This is standard normal distribution. As far as the graph, we want this area, which is clearly large. And that's 0.9772. Mu of x bar refers to the mean of the means, and sigma of x bar means the standard deviation of the means, okay? And so if we were to do it by technology, okay, and I want to go back to the first one, this one. Lower, so we're going to use normal CDF. Lower class, since they have already used the number, we're going to stick with that. And by the way, E means times 10 to the power of that, and it's negative, okay? This has a negative value that it's hard to see. If it's not given, this really goes from negative infinity to 6.2. And therefore, what you want to do, you want to write minus 1,000. That's good enough. I've already explained that to you. You can go back to the notes. And so if you plug in the number that it gives you, within 4 decimals are the same. This is using table. This is using technology. For the second case, the same lower again, upper is 6.2, mu is 6, but sigma is 1 over 100 to the power of 0.5. That means square root of 100. Okay, so again, I wanted you to see side by side. The thing that changes is sigma. And the result is what we have here within 4 decimals, 1, 2, 3, 4, they are identical. Okay? The table does a pretty good job. Could somebody read this question, please?
The assets in billions of dollars of the 4 wealthiest people in a particular country are 33, 29, 16, and 11. Assume that samples of size n equal 2 are randomly selected with replacement from this population of 4 values. A. After identifying the 16 equals 2 to the 4th power, different possible samples, and finding the mean of each sample, construct a table representing the sampling distribution of the sample means.
Thanks. The reason I've chosen a small number because if we want to go with the sampling distribution of the sample mean, it's going to be very difficult when you have a large size. So here's the concept. So if we choose 33 and 33, everybody. So I want you to look at the very top. If we choose 33 with 29, 33 with 16, and 33 with 11. Then we go with the second number. We choose 29 with 33, then 29 with itself 29, then 29 with 16, then 29 with 11, and we continue with the next one. There's not enough room, but you get the picture when I do those. Now, I come back to the first. What is the average here? Add them up, divided by 2. What is the average here? Add them up, divided by 2, and it continues indefinitely, right? There are actually 16 of them, not indefinitely. So this is X bar, everybody. This is X bar. So we are taking the average of these two. Now, probability of X bar, there are 16 outcomes. Each one has a possibility of 1 out of 16. There are 16 of those when you write all of them. I put 4 and 4, 8 of them. There are 8 more. Just for the sake of argument, the next number is 16. 16 with 33, 16 with 29, 16 with 16, 16 with 11. Last one is 11. 11 with 33, with 29, with 16, and itself. Those are the others. So what happens now, I want to write the probability distribution for that. So take a look at how that works. We have X bar and P of X bar. So starting with 33, there is only 1 out of 16. But what about 31? When you look at this one, class, 31, the average of 33 and 29 is 31. If you reverse them, the average of 29 and 33 is also 31. So that's why for 33, we have only one choice, 1 out of however many, to the power of 16. But something like 31, we have 2 of it. 1 and 1, it's 2 over. I didn't want to write 1 over 8. Everybody knows it's 1 over 8. And if you were to represent that as the final answer, the answer is 1 over 8. But I wanted you to see why, when you look at the number itself, it's 1 out of 16, 29, 1 out of 16, okay? 16, 1 out of 16, 11, 1 out of 16. But the other averages, there are 2 out of 16, okay? Now, this is called the sampling, a table representing the sampling distribution of the sample means. This is the sample you picked, right? And the sample means is 1 over 16 for this pair. The sample mean for this pair is different, happen to be the same as this one. And this is the sampling distribution. By definition, sampling distribution for discrete random variable is X bar and probability of X bar. Now, we want to compare the mean of the population to the mean of the sampling distribution of the sample mean. Let me tell you what that means. The mean of the population, go back to those 4 numbers, 1, 2, 3, 4. How do you find the mean? Add them up, divide by 4. So that's mu. Mu is summation of X divided by capital N. Add them up, divide by 4, and that's 22.5. This is the mean of the population. So the population has only 4 members, 4 subjects. Add them up, divide by 4. Done. The second part says the mean of the population. We want to compare it to the mean of the sampling distribution. So we want to look at the mean of the sampling distribution. How do we find the mean for this table? Mu of X bar is summation of X bar, P of X bar. In other words, this number times this, plus this number times this, plus this number times this, all the way to the last one, right? That is what we have learned. It so happened it becomes identical. So they are equal. Mu is equal, this is called mu of X bar, mu of X bar. The mean of the sampling distribution, mu of X bar, is identical to mu. Do the sample means target the value of the population? In general, do sample means make good estimates of population mean? Why or why not? the sample means target the value of the population mean. That is, the mean of the sample means, the mean of the sample means is mu of x bar. The expected value of the sample mean is equal to the population mean. Mu of x bar equals mu. So that's how you estimate it. That's where your sample means, can target the value of the population mean because they end up being identical. All right. Could somebody read this for us?
The population of current statistics students has ages with mean mu and standard deviation.
Sigma.
Sigma, thank you. Samples of statistics students are randomly selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does central limit theorem tell us about the distribution of those mean ages?
Thanks. Central limit theorem, or CLT. The central limit theorem, a sampling distribution of sample means is a distribution obtained by using the means computed from random sample of a specific size taken from a population for samples of size n larger than or equal to 30. That's important when n is large. How large is large? N is larger than or equal to 30. The distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. The bottom line is, when we have a larger sample size, the better the approximation. I hope everybody understands. It's very simple. We don't have access to the population, so we have to pick a sample. If we have means so that we can pick a larger sample, it works out better. That's really the bottom line here. So here's the conclusion. The distribution of sample X bar will, as the sample size increases, approach a normal distribution. As sample size increases, this approximation gets better and closer to a normal distribution. The mean of a sample means is the population mean. We showed in the previous page, mu of x bar is equal to mu. That's what we are saying. So pick a sample, okay? And if you have the sample of the same size, each sample may have a different x bar. Add up all those x bars and divide by the total size, it becomes the same as mean. The standard deviation of all sample means is sigma of x bar equals sigma over square root of n. And so for this question, since n is 44, which is larger than 30, a sampling distribution of the mean ages can be approximated by a normal distribution with a mean of mu of x bar equals mu, and standard deviation of sigma of x bar is sigma over square root of n, so sigma over whatever that number is, square root of 44. Could somebody read this question, please?
A boat capsized and sank in a lake based on an assumption of a mean weight of 137 pounds. The boat was rated to carry 50 passengers. So the low limit was 137 times 50 equals 6,850 pounds. After the boat sank, the assumed mean weight for similar boats was changed from 137 pounds to 170 pounds. A. Assume that a similar boat is loaded with 50 passengers, and assume that the weights of people are normally distributed with a mean of 174.1 pounds and a standard deviation of 35.1 pounds. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds.
Excellent. So this is quality control. This is checking whether the old assumption works or not. So as we read this question again, it's a word problem. Let's quickly figure out what is a given. It's a normal distribution. N is 50. The mean, or in this case, mu, is 174.1. Standard deviation, or sigma. It is extremely important to write the proper symbols. Greek letters represent the population. So what do we want to check? Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137. So probability of X bar larger than 137. So again, please understand, we may have to read this a couple of times to write this. And when we write this, we are, and of course this one, we are practically done because the rest is very simple. Z is X bar minus mu of X bar over sigma of X bar. So we're going to replace this with 137. Mu of X bar is the same as mu. Mu of X bar is the same as mu, so 174.1. Sigma of X bar is sigma over square root of n. So 35.1 over the square root of 50. So let me just quickly write this. So mu of X bar is mu, and sigma of X bar is sigma over square root of n. And when you do the math, you end up with negative 7.474. Probability of Z larger than that number, it's almost one class. That negative 7.474 is way beyond the negative 3.5. Remember, within three standard deviations on both sides, we cover almost everything, 99.7%. So this covers one, and you can even use technologies to see that's the answer. So 100% almost. So the probability that the mean is larger than 137 is huge. It's 100%. Now, the boat was later rated to carry only 15 passengers. Notice, from 50, we're going to go to 15. This is quality control, saving people. And the load limit was changed to 2550, which means 170 times 15, okay, or 2,550 pounds. Now find the probability that the boat is overloaded because the mean weight of the passengers is greater than, now we are changing the number to 170, so that their total weight is greater than the maximum capacity of 2550. So again, we are dealing with normal distribution. Everything is the same here except n has changed. Everybody, n has changed from 50 to 15. But it's the same situation. So we want probability of X bar larger than 170. We are going to use the same formula. X bar is 170, and these two are the same. And this gives us negative 0.4524. And using either technology or the table, we end up with 0.6745, 67.45%. Do the new ratings appear to be safe and when the boat is loaded with 15 passengers? No, this is pretty large class. No, because there's a high probability, 67.45%, of overloading, the new ratings do not appear to be safe when the boat is loaded with 15 passengers. At an airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 10 minutes. All of the different possible waiting times are equally likely. Find the probability that a randomly selected passenger has a waiting time of at least 7 minutes. First, we want to discuss the uniform distribution. Can somebody read the information about uniform distribution, please?
A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. Properties of uniform distribution. Density curve. The graph of any continuous probability distribution is called the density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. Therefore, probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area equals height. Height times width.
Excellent. The total area is 1 because the total area represents the probability. And we're going to go from 0 to 10. So the total area under the curve is 1 because it represents the total probability. And the width is 10 minus 0 or 10. So the height must be what? 1 over 10. So the height must be 1 over width or 1 over 10 or 0.1. So again, if this is 10, this must be a number such that their product must be 1. Now, the product of these two must be 1. That's how we arrive at it. This is 5, this is 1/5. Okay. This is 2/3, this is 3/2. Their product must become 1. That's the bottom line. And so if this is 10, this must be 0.1 because the area must be 1. That's understanding the question and the concept of a uniform distribution. First, uniform distribution. The height doesn't change. Now, find the probability that the randomly selected passenger has a waiting time of at least 7 minutes. Probability of x larger than or equal to 7. So probability of wait time of at least 7 minutes means probability of x larger than or equal to 7. So from 7 to 10, that's the shaded region. And all you have to do, find this area. Find the area of the shaded region, which is the height, which is fixed at 0.1 times this width. Now, because we go from 7 to 10, this must be 10 minus 7 or 3. So their product is 0.1 times 3 equals 0.3. 30% of 0.3. So what is the probability that a randomly selected passenger has a waiting time of at least 7 minutes, that means 7 minutes or more, is 0.3 or 30%. Could somebody read this one, please?
Information regarding standardized tests used for college admittance. Scores on the SAT test are normally distributed with a mean of 984 and a standard deviation of 204. Scores on the ACT test are normally distributed with a mean of 20.7 and a standard deviation of 4.3. It is assumed that the two tests measure the same aptitude, but use different scales. If a student gets an SAT score that is the 65th percentile. Find the actual SAT score, the whole number.
Thank you so much. They want us to round it accordingly. Okay, so first and foremost, what is given when we read this question? So we go back to up here and we notice that the mean is 984, standard deviation is 204 for SAT. So mu is 984 and sigma is 204 for SAT scores. So that's the given. For ACT scores, the mean mu is 20.7 and standard deviation sigma is 4.3. So those are given so far. A student gets an SAT score. We are here. That is 65 percentile. That means if we go with normal distribution, the area it covers is 65% or 0.65. So this is the coverage. Okay. And by the way, as you can see, it's the right of 0 because it's larger than 0.5. So what is the concept? The area to the left is 0.65. We're going to find the z-score, and from the z-score, so first we're going to find the z-score here. So this area, what color do I want to use? Let's say this one. This area, everybody, is 0.65. So we are going to find this z-score here. Then from the z-score, we're going to go to the x value. Remember, z is x minus mu over sigma. So we are going to find the z-score first. And from z, we are going to go to x. We know z is x minus mu over sigma. And if you do the cross product, x becomes mu plus z sigma. I hope everybody's comfortable with that. This is fairly basic. X is mu plus z sigma. We are going to use that. What information are we using? SAT scores. We are going to use mu equals 984, sigma equals 204. So plug in. To plug in, we need to find the z-score first. Whether you use technology or table makes no difference. So if we go with the technology area, we use inverse norm. Area is 0.65, mu is 0, sigma is 1, and we end up with this number as the z-score. So over here we have the mu, we have the sigma, and now we have the z as well. And you want to use many decimals, and we end up with 984 plus 0.3853 times 204 is 1062.61. They said go with the whole number because this is number 6. We're going to change this to 3. So the answer is 1063. They're pretty straightforward. What would be the equivalent ACT score for this student? So in essence, we want the X value for this case class. We need to find the Z value here. We already have it. So we are going to use this Z value. So look at this formula. This formula class, we need mu, Z, and sigma. We use the same Z for this part. Mu and sigma, we use it for ACT because that's what they say. Now, in both cases, The z-score is 0.3853, whatever. So we are going to use this information and this formula, same z. Mu is 20.7, sigma is 4.3. Plug it in here with the same z value as the previous part. So 20.7 plus 0.3853 that we used here, because we ended up with 4 decimals, times 4.3, this is 22.36. And it says, in this case, use 1 decimal. So we want to use 3, next to it is 6, we take it up. Becomes 22.4, which means SAT score of 1063 is equivalent to ACT score of 22.4. That's the meaning of it. And they both have the same z-score of 0.3853204 and continues. If a student gets an SAT score of 1494, so over here, the SAT score is 1494, the X value here is 1494. Find the equivalent ACT score. So from here, okay, up here, use the process to find the z-score, and then from the z-score of SAT, go to the X value of ACT. That's the concept. So for SAT, X is 1494. We need to find the Z. After we find the Z, we go to the X value for ACT. That's the process, everybody. So Z is X minus mu over sigma. X 1494 minus mu 984 over sigma 204. So SAT score of 1494 corresponds to the Z score of 2.5. So we need the same Z score for ACT, and we use this formula. X is mu plus Z sigma for this one. So use mu and sigma from here, use the Z score from here. So X is 20.7 mu plus 2.5 times 4.3 equals 31.45, and again with 1 decimal 4 changes to 5. Again, pretty straightforward, everybody. In short, SAT score of 1494, an ACT score of 31.5, and a Z score of 2.5 are equivalent. So it is the Z score that will help us go from one to the next. Could somebody read this question, please? We have 2 more questions to go. This is one of them, class. Could somebody read this, please?
A food marketing institute found that 35% of households spend about $150 a week on groceries. Assume the population proportion is 0.35 and a simple random sample of 300 households is selected from the population. What is the probability that the sample proportion of households spending about $150 a week on groceries and less than 0.38?
Excellent. Again, we read the question, what is given? what is the question all about? So we have to read and reread. This is a binomial distribution with the proportion being 0.35% and n is 300. N is 300. Because the concept is you either spend 150 bucks or you don't. There are two outcomes. Now, we want the probability of a p hat is larger than 0.38. And I will discuss this further in the next question, which is similar to that with different methodologies. So probability of a p hat less than 0.38, that's what this says. We want to calculate the probability of p hat less than 0.38. Information about p hat. So first and foremost, NP and NQ are large. If you multiply these two, is larger than 10, and Q is 1 minus 0.35 or 0.65 times that is even larger. So the product, I didn't show that, but you can clearly see 300 times 0.35 is 105, which is larger than 10. And so we can approximate it by normal distribution. Also, we know mu of p hat is p sigma of p hat square root of pq over n. You can go back to your formula sheet. Therefore, mu of a p hat equals a p or 0.35. So this is 0.35. And sigma of p hat 0.35 times 0.65 divided by 300. Plug in because we need to calculate. These are preliminary calculations we need to do. So this is 0.35 and this one using a calculator with a bunch of decimals. We end up with this number. Now there are different ways of approaching this. If you want to use a calculator, you can say p hat less than 0.38 and use this information. The lower is like minus 1,000. I've told you that before. Okay. But if it gives you an answer already, this means to the power of 10 to the power of 99 with a negative, okay? Which is like, but minus 1,000 will do the job. What is the upper is 0.38. So this is from negative infinity to 0.38. Mu is mu of p at or p, 0.35. Sigma, we just calculated it. If you plug in, that gives you the answer. Or go with z equals x minus mu over sigma, which is p hat minus p over sigma of p hat, according to this formula. P hat minus p over sigma of p hat. P hat is 0.38, p is 0.35, sigma of p hat is 0.027538. And that will result in 1.0894. So probability of p hat less than 0.38 is the same as probability of a z less than the number we just calculated. And with that, if we were to calculate this, the upper would be this number. Mu is 0. This is SND, standard normal distribution, 0 and 1. And when you do that, notice what happens. Those, we put it there with 4 decimals. Okay. These two are almost identical. It depends, how far you go with your decimal, by the way. Okay. And so 0.8620. So what is the probability that the sample proportion of households spending about $150 a week on groceries is less than 0.38 or 38%? is 0.8620 or 86.2%. What I want to do, I want to look at this last question, which is similar to that from different points of view. This is similar to that. According to a survey, 10% of Americans are afraid to fly. Suppose 1,100 Americans are sampled. What is the probability percentage that 121 or more Americans in this survey are afraid to fly? Well, it's a binomial distribution. P is 10% and is 1,100. Why is that? Because there are two outcomes. You're afraid to fly or you're not. Either or. So it makes it binomial distribution. Probability that we are afraid is 10%, and we have chosen N to be 1,100. So we're going to go with different methods, 3 methods. So here's one of them. X is 121, right? 121 or more. P hat makes it X over N. So the proportion for this sample, if we had 121, would be 0.11 or 11%. And what we want is the probability of P hat larger than or equal to 0.11, because let's go back to the question. What is the probability percentage that 121 or more? That means 11% or more. That's the proportion, right? That's the sample proportion. 121 out of 1,100 gives us 0.11. That is 121 or more in the survey are afraid to fly. So this is what we are looking for. Okay, let's do that. Mu of P hat is P, just like before, which makes it 0.11. My apologies, makes it 10%, 0.1. Sigma of P hat is square root of PQ over N. P is 0.1, Q is therefore is 0.9, right, class? Maybe I write it right here. Okay. So P is a 0.1, Q must be 0.9, 1 minus that. So we calculate those, and this ends up being 0 with a bunch of decimals, 0.00904553. So if I want to go with the technology, take a look at the way we use the technology. We want probability of P hat larger than or equal to 0.11. So the lower is 0.11. The upper is 1. Let me explain about the upper here. Even if you use 1,000, it works. But the reason I used 1, and I want to make sure everybody understands that this is a binomial distribution. This is a proportion. Proportion can't be larger than 1. So although it doesn't recognize this, it recognizes that as a normal distribution, but I want to tell you why I used 1, because we're dealing with P and P hat and so forth, and proportion can't be larger than 1. Mu is 0.1, and sigma of P hat is this number. When you do the math, gives you this answer. Now I want to hold on to that, and I want to quickly go over other methods. Again, you can use 1,000 again, because the technology is not recognizing you're dealing with a proportion. And remember, the upper, you can make a large number here because you want it larger than that. It will give you the same answer. Plus, this will give you the same answer. The reason 1 works here and it won't otherwise is because you're dealing with proportion. Can't be larger than 1. That's why. That's the maximum value for that. If you're not too sure that it's a proportion, of course, you have to go with 1000. Method 2, we calculate the z-score using p hat minus p over sigma of p hat. So 0.11 minus 0.1 over this number. That gives you that. So probability of z larger than or equal to this number. So this is equivalent to this if we use the z-score. Method 3, using binomial distribution, probability of x larger than or equal to 121. This is what we have seen, and the concept of a 0.5 continually correction factor. Okay, remember what we do. We either add or subtract 0.5. If I add 0.5, I get 121.5. And remember this one, let me just write that because it's important to know what that means. This means probability of x equals 121 all the way to probability of n, which is 1100. The first one is 121, everybody. The first one is 121. So if I use 121.5, the first one larger than that is 122, and I'm going to lose 121. So we must go with 120.5. I hope everybody understands this. Again, going back to the continually correction factor of 0.5, you have to do that because we go from a discrete to continuous. And now, this one is the x. We are going to change it to a z, x minus mu over sigma. X is 120.5. Mu is np or 110. Sigma is square root of npq, plug in 1100 times 0.1 times 0.9. So we have a different mu sigma, plug it in here. And it so happened it gives you basically the same z-score as this one, almost the same class. So with binomial distribution, normal distribution, now is S and the standard normal distribution, and both of them are almost the same, using technology, lower is this number, upper. Now this one you cannot use 1, unlike this one that we could, because we're dealing with proportion. This one you must use 1000 or 10,000 or even 100 might do the job. And this is the answer. Now take a look at this one, and the final answer with 4 decimal 0.134. This one is 4, next to it is 6, we take it up to 5. And they all give you the same answer. So I wanted you to be exposed to different methods here. Same question, every calculation from the previous pages here, which we need. What is the probability percentage that 165 or more Americans in the survey are afraid to fly? Well, we can either go with the method, the last method we use, or the first one. P hat is x over n, makes it 165 over 1100 or 0.15. And we want the probability of p hat larger than or equal to 0.15. We calculate the z. As p hat minus p over the sigma of p hat, gives us this number, 5.52773. We put it here, and if we use a calculator or any technology, we can say lower 0.5, upper is 1, mu is 0.1, and we get this answer. Now notice, I wanted to show you here. Remember, the reason I'm using 1, because I'm using p hat, and therefore the upper is 1. As I said, the technology doesn't recognize it. If instead of 1, I put 10,000, Okay, both of them will give us the same answer. Or in this case, if we go with the z-score of 5.52773, when we go with this one, everybody, with this one, we must use 1000. And I, on purpose, I've used 1000 here and I used 10,000, two different numbers. My point is 1000 is good enough. Why? Because within 3 standard deviations on both sides, we cover almost everything. That's why 1000 is way too large. Even 100 may do the job. And all of them will result in this answer, okay, e to the power minus. I want to make sure you understand what this means. This is almost zero, but if I were to write this means the following. This means 1.626 times 10 to the power of minus 8. Which means what? If I were to write it as a decimal, this decimal, this is the first one, number 1, and then I go 7 more to make it 8. So I have to go 8 of them. So this decimal point must move this way. How many decimals? 8 to the left. And you add 0, 0, 0. So I have 0.7 zeros and then 1, which is almost 0. That's the meaning of it. Sometimes students put it into a calculator, they don't know the meaning. This is a scientific notation, everybody. This is a scientific notation. If I wanted to go with the third method, normal distribution, this would have been, let me just write this here. This would have been the probability of X 165 or more, which means probability of 165, and it continues indefinitely. So this is binomial distribution. To go with normal distribution, we either have to add 0.5 or subtract. If I add 0.5, if I get 165.5, the next number is 166, and I'm going to miss 165. So it has to be larger than, whether you put the equality or not, it doesn't matter, 164.5. Okay, if you were to use that methodology, this is a 0.5 continually correction factor, and you can do it that way. Okay. Of course, you have to calculate the z-score as you did in the previous page. We have the mu and sigma for that as well. And finally, what is the probability percentage that 8% or less of the Americans surveyed answered they were afraid to fly, round the percent to 2 decimals. And so we want the probability of p hat less than or equal to 0.08. Because of that, I didn't want to go with that method because the 2 parts use that. So we can stick with that. And if we go with the technology, okay, lower is 0, upper is 0.08, mu is 0.1, sigma is the number with a bunch of decimals. And here's the second method. Again, why am I using 0? Because I know it's a proportion and the proportion is between 0 and 1. Can it be 0? Yes. Can it be 1? Yet, but it can't be negative. It can't be larger than 1. However, the technology doesn't recognize it. So for the lower, you might use minus 100, minus 1000, minus 10,000. Both of them will result in the same answer. And if we write it as 1.35%, it's just as good.